So suppose that we have got a certain amount of ice, say some 1 kilogram, and we keep adding heat to it. Okay, it will start melting. Now the temperature of the melted water will not start rising until the whole of the ice has got melted. Means there will be no change in the temperature during a phase change, or we can say a phase change is an example of a constant temperature thermodynamic process. Otherwise we call it as an isothermal process. So until the phase change is complete, whether it is moving from say solid to liquid or from liquid to gas, the temperature of the substance remains constant. So let us try to understand why the temperature doesn't change during a phase change. Okay, so for that let us consider the two different types of phase transitions. Let me consider the solid to liquid transition first. So let's say that I have got certain amount of substance in the solid phase or solid format. So what I'm doing is that I'm adding say some amount of heat to it. So I'm adding some heat to it. Let me add say Q amount of heat to the solid sample. Let me say the mass of the sample be M. So what happens is that the solid starts getting converted into liquid. Okay, like ice is getting converted into liquid water. Now during this process I can say the heat required for melting, heat required for melting the sample, you can see that it is directly proportional to the mass of the sample. That is a very common observation, logical also. You can see mass of the sample. It means that if you have got a large amount of sample, then you will have to supply more amount of heat. That is very clear. Okay, so heat required for melting, which is a phase change, it is directly proportional to the mass of the sample. Greater the mass of the sample, greater will be the heat required for melting it completely. Okay, now what I can do, I can write the heat required as Q. So Q is directly proportional to M. Is that the thing? Q is directly proportional to the mass of the sample. Now what I can do, I can replace this proportionality with a constant of proportionality, and introducing that constant as L, and let me write it for the timing as LF. F stands for fusion, LF into EM. So Q is equal to, the heat required is equal to LF into EM. That is the equation, where this LF is the quantity known as the latent heat of fusion. You are already familiar with this term. I just remind you again, latent heat. L stands for latent heat, and this F denotes melting. Otherwise I can call fusion, latent heat of fusion, or melting also you can say, latent heat of fusion. Okay, so let's try to understand what is meaning latent heat. So as we have discussed before, as long as the process of melting is not complete, the temperature of the substance, solid substance, will not rise. Okay, for example, this is, say that this is ice you have taken, and let's say that the temperature of ice is what, 0 degrees Celsius. Ice at 0 degrees Celsius. Even below 0 degrees Celsius also it will be existing in the solid state. Ice at 0 degrees Celsius. You are going on giving, say that suppose that I have got 1 kilogram of ice, I'm going on heating ice in order to convert this 1 kilogram of ice completely into, what is that, the mass is conserved, you can say. So 1 kilogram of liquid water, you have to provide certain amount of heat. You have to provide certain amount of heat. Okay, and that heat is what is known as the latent heat. And during this process of phase transition, you can see the temperature is remaining constant. The temperature is remaining constant, or it is an isothermal process. So automatically the question comes, where does this heat go? Where does this heat go? You are giving heat to the system, and the temperature of the system is not increasing. You are providing heat to the system, but the temperature of the system is not increasing. Okay. But you know that in this process, actually the internal energy of the system will be increasing, but that doesn't result in an increase in the corresponding increase in the temperature. So what actually is happening is that the heat that you are supplying to the solid will be converted not into the kinetic energy of its constant particles, but it will be used to overcome the intermolecular cohesive forces. Okay, so it will be just, you know, that's a what is known as the potential energy. So actually what happens is that heat given will be used up for just changing the potential energy, not the kinetic energy. Okay, so what happens here is that there won't be any rise in the temperature. Instead, the molecular nature of the molecular interaction, means the potential energy of the interaction, will be undergoing change. Since it is potential energy which is changing, there will not be a change in the temperature. Instead, the temperature will be remaining constant. So you can always remember a phase change as the best example of an isothermal process. Okay, now let us see what is the meaning of this ELF. So let's say latent heat of fusion, L, or LF, it will be equal to Q divided by EM. Okay, Q divided by EM, that is the definition. So if you see the unit of this one, either you can say joule per kilogram, or a common unit is calories per gram. Calories per gram, that is a common unit of latent heat that is usually expressed. For example, you consider the most common case of for ice to water transition. For ice to water transition, there should be a latent heat of fusion, as we examine. So you will see from experiments that this latent heat of fusion in the case of ice to water conversion is 80 calorie per gram. 80 calorie per gram. So you can clearly understand what's the meaning of this data. What's the meaning of this data? The meaning is that it requires 80 calories of heat. You have to supply 80 calories of heat to convert 1 gram of 80 calories for converting 1 gram of ice. 1 gram of ice at what degree Celsius? At 0 degrees Celsius. 1 gram of ice at 0 degrees Celsius completely into, what is that? 1 gram of liquid water. 1 gram of water at that to at what? 0 degrees Celsius. Same temperature. Okay. So you are converting 1 gram of ice, a block of 1 gram of ice, completely into 1 gram of liquid water. For that you need to supply 80 calories. Okay, you can express it in joules. You know the conversion factor. Okay, 1 calorie is equal to 4.2, roughly 4.2 joules. So you can express it in joules per gram or joules per kilogram, doesn't matter, depending on whatever units that you are using for other quantities. So you can understand this value. See that you memorize this value for water to ice, or sorry, ice to water conversions. And the same manner you can talk in the reverse way also. Okay, when you solidify, you say that when you are solidifying 1 kilogram or 1 gram of water to ice, automatically what will happen? Instead of heat being absorbed, heat will be released. Okay, so I can say basically what is meant by latent heat. Basically, latent heat is the energy. So I can say that latent heat basically that is the energy, heat energy. Usually we say heat energy, either I can say absorbed. In the case of ice to water transition, it is absorbed, and that is used for overcoming the intermolecular cohesive forces. Okay, absorbed, and it can be even released. Okay, in the reverse case, when water is turning freezing to ice to form ice, so certain same amount of heat will be getting what released. So latent heat is the energy absorbed or released by a system, by an object, you can say, or by a thermodynamic system. Let's make it a very general textbook definition. By a thermodynamic system, okay, during a phase change. I think that can be the best definition, during a phase change. And you know, phase change is an isothermal process, that is T equal to a constant. So that is automatically a question. Okay, what happens, or why the temperature remains constant during phase change? Okay, എന്തുകൊണ്ടാണ് ഒരു വസ്തുവിൻ്റെ ടെമ്പറേച്ചർ ഫേസ് ചേഞ്ച് കംപ്ലീറ്റ് ആവുന്നത് വരെ കോൺസ്റ്റന്റ് ആയി നിൽക്കുന്നതെന്ന് ചോദിച്ചിട്ടുണ്ടെങ്കിൽ അതിന് ഒരേ ഒരു ഉത്തരം എന്ന് പറയാനുള്ളൂ. എന്താണ്? ദാറ്റ് മച്ച് എമൗണ്ട് ഓഫ് ഹീറ്റ് എനർജി ഈസ് absorbed as the latent heat. Means in order to change the intermolecular force of attraction, you will have to use certain amount of energy. അപ്പോൾ ഹീറ്റ് സപ്ലൈ ചെയ്യുമ്പോൾ നമ്മൾ സാധാരണ പ്രതീക്ഷിക്കുന്നത് എന്താണ്? അതിന് പ്രൊപ്പോർഷനേറ്റ് ആയിട്ട് ടെമ്പറേച്ചറിൽ ഒരു ഇൻക്രീസ് ഉണ്ടാവണമെന്നാണ്. അപ്പോൾ ഹീറ്റ് സപ്ലൈ ചെയ്തിട്ടും ടെമ്പറേച്ചറിൽ ഇൻക്രീസ് വരുന്നില്ല എന്ന് പറഞ്ഞാൽ അതിൻ്റെ അർത്ഥം ആ കൊടുക്കുന്ന ഹീറ്റ് ഇറ്റ് ഇസ് ജസ്റ്റ് ലൈക്ക് ഇറ്റ് ഈസ് എ സ്ലീപ്പിംഗ് ഹീറ്റ്. Okay, that heat is not able to make any impact on the temperature of the system. അതുകൊണ്ടാണ് ഇവിടെ എന്ത് വാക്ക് ഉപയോഗിക്കുന്നത്? അത്തരത്തിൽ ടെമ്പറേച്ചറിൽ വർധനവുണ്ടാക്കാൻ കഴിയാത്ത ഹീറ്റിനെയാണ് നമ്മൾ ഇത് വിളിക്കുന്നത്. We call it as what is known as the latent. Latent, you know that latent means hidden or sleeping എന്നുള്ളൊക്കെ അർത്ഥത്തിലാണ് latent. Okay, latent potential എന്ന് പറയുന്നതല്ലേ ഒളിഞ്ഞിരിക്കുന്ന എന്നൊക്കെ ഒരു അർത്ഥത്തിലാണ്. സ്ലീപ്പിംഗ് ഓർ ഹിഡൻ എന്നൊക്കെയുള്ള മീനിങ്ങിലാണ് ലേറ്റൻറ്റ് എന്നുള്ള വാക്കിൻ്റെ അർത്ഥം. ഓക്കെ, സോ യു ക്യാൻ അണ്ടർസ്റ്റാൻഡ് വൈ ഇറ്റ് ഇസ് നോൺ ആസ് ലേറ്റൻറ്റ് ബിക്കോസ് ദാറ്റ് അങ്ങനെ ഒരു ഹീറ്റ് വസ്തുവിലേക്ക് കിട്ടിയെന്നുള്ളതിനുള്ള യാതൊരുവിധ തെളിവും അത് സിസ്റ്റം അവശേഷിപ്പിക്കുന്നില്ല എന്നുള്ളതാണ്. ഓക്കെ, ഉണ്ടാവേണ്ട തെളിവ് എന്താണ്? ടെമ്പറേച്ചർ വർധന. പക്ഷേ ദർ ഇസ് നോ എനി ചേഞ്ച് ഇൻ ദ ടെമ്പറേച്ചർ. സോ ദാറ്റ് ഇസ് എ മീനിങ് ഓഫ് വാട്ട്? ലേറ്റൻറ്റ് ഹീറ്റ് ഓഫ് ഫ്യൂഷൻ. ഓക്കെ, ലേറ്റൻറ്റ് ഹീറ്റ് ഓഫ് fusion. So just memorize this value for water. It is 80 calories per gram. Now in the same manner we can discuss what is meant by latent heat of vaporization. Same manner you can just discuss the liquid to gas transition. Liquid to gas transition. So same manner you can just discuss. Suppose you consider that you have got some m mass of a liquid, at certain temperatures is that T. Okay, and what you are doing, you are supplying certain amount of heat to it. Q amount of heat കൊടുക്കുകയാണ്. So what happens is that let the liquid be at its boiling point. The liquid be at its boiling point. For example, for water, let me say that the liquid is already at 100 degrees Celsius. Okay, or 373 Kelvin. Now what happens, you know that once you begin to give heat to it, it begins to get vaporized. It will be getting converted into vapor, and the temperature of water will not increase beyond 100 degrees Celsius until the entire amount of liquid water in the container has got converted into what you say that vapor, right? And that is why we say that during boiling the temperature remains a constant. So boiling it is a process where liquid is getting converted into gas, right? So ഈ പാത്രത്തിലുള്ള മുഴുവൻ വാട്ടറും അല്ലേ എന്താണ് കൺവേർട്ടായി തീരുന്നത് വരെ എന്ത് ചെയ്യുന്നില്ല, ഇവിടെ ടെമ്പറേച്ചറിൽ യാതൊരുവിധ വർധന ഉണ്ടായിരുന്നു. സോ വൺസ് അഗൈൻ യു ക്യാൻ റൈറ്റ് ദ റിലേഷൻ ലൈക്ക് വാട്ട് യു ഹാവ് ഡൺ ബിഫോർ. സോ വാട്ട് ഇസ് ദാറ്റ്? ദ എമൗണ്ട് ഓഫ് ഹീറ്റ് റിക്വയർഡ് Q will be directly proportional to what? The mass of the substance, right? So heat required for vaporization is directly proportional to the mass of the sample. So what you can do, you can just equate it. Q is equal to some proportionality constant L into M. Earlier also it was L into M. So now this is the process is vaporization. So I'll name it as what? LV into M, latent heat of vaporization. So automatically, you know, LV will be equal to Q divided by M. It's same quantities as we are defined. So it will be once again expressed in calories per gram, right? Calories per gram. And for water to steam transition, so some data for water to steam transition or vaporization. Okay, for water to steam transition, the latent heat of vaporization, that's roughly 540, very near to 539 something. I can round it up, 540 calories per gram. Calories per gram. Hold the units, calories per gram. Okay, what's the meaning? If you have got a 1 gram of water at its boiling point, that is the meaning of that. Okay, that is you have got a 1 gram of liquid water. Okay, at what temperature? At its boiling point, at 100 degrees Celsius. It should be at the boiling beginning of the what do you say that vaporization process. To convert this one entirely into what is that? Steam. Entirely into steam. Okay, steam at the same temperature at 100 degrees Celsius. Okay, it's not any super saturated or anything. You have to supply how much? Okay, for 1 gram you have to supply how much? 540 calories. This is the meaning of latent heat of vaporization. 100 degree സെൽഷ്യസിലുള്ള തിളനിലയിലുള്ള അല്ലെങ്കിൽ 100 ഡിഗ്രി സെൽഷ്യസിലുള്ള 1 ഗ്രാം വാട്ടറിനെ കംപ്ലീറ്റ് വേപ്പറൈസ് ചെയ്ത് മാറ്റാൻ വേണ്ടി എന്താണ് നിങ്ങൾ എത്രത്തോളം ഹീറ്റ് എനർജി സിസ്റ്റത്തിലേക്ക് സപ്ലൈ ചെയ്യണമോ ആ ഹീറ്റ് എനർജിയെ എന്ത് ചെയ്യുന്നു? വി കോൾഡ് as what is known as the latent heat of vaporization. Hope you can clearly understand what's meaning in latent heat, and we will just do a problem. Okay, so that you can understand the concept of latent heat and how it is applied in a problem involving phase change. That we'll do in the next video. Okay, thank you.